Today on Dino Diladon, we'll be taking a look at the Obis Core LS, which is a miniaturized optically pumped semiconductor laser manufactured by Coherent. Now, I can't say this is ultra miniaturized because smaller optically pumped semiconductor lasers have been manufactured. However, given some of the other ones that Coherent has made, we can definitely say that that laser is quite compact. And now for the question on everybody's mind, what's the actual size of this coin? Now, before I can make any attempt at getting this little laser head operating, there are two things I need to add. Number one is an external heatsink to make sure that the laser head doesn't overheat. And number two is a thermoelectric cooler. Now, the only reason why I need this is because the thermoelectric cooler on the inside of this laser head that normally maintains the temperature stability of the optically pumped semiconductor laser is broken. So I'll be using this external one instead. I'll talk a little bit more about that in the video, but for now, let's go ahead and get this whole thing put together. And like with most lasers, you want to go around, make sure you don't clamp down the screws too hard, that way you don't ruin the alignment or crack anything that might be connected on the inside of the laser head, or make any clicking, crunching sounds out of the junctions in the thermoelectric cooler. Alright, well, that looks good. Let's start connecting some electronics. The first thing I'm going to electrically connect is a constant current driver to the Pump Laser Diode on the inside of the laser head. So I want to point out on the back that there is a little Schottky diode that is used for reverse protection and goes across the Pump Laser Diode. So in this case, I have a white wire connected to the cathode and I have a blue wire connected to the anode. And I'll be using this to get a voltage reading of what's going across the junction. The reason why I'm doing the reading there is because I want to avoid any kind of confusion with a voltage drop that might be present on the cable. And what I mean by that is if this laser requires 2 volts and I'm doing my reading here, I might read 2 volts here. But as the power goes through the cable, some of it might be used in that cable and the voltage might drop. And I might say get only 1.5 volts here. So to minimize that confusion, I'm going to do my reading as close to the Pump Laser Diode as possible. It's just good practice. Now, as far as the pinout on the back connector here, I didn't work out most of it, but instead that was done by a viewer. Same viewer who let me know that these were purchasable. So big thanks to him on his effort. So this is the original cable that I made to verify the pinout, which is quite intimidating, but after figuring out what I needed, I made a much friendlier looking cable. So I'm going to go ahead and use that. Don't worry, the full pinout will be revealed, or at least the parts you need. Just like that. Let's make sure that it's actually connected properly. I'm going to throw this in diode check mode, and I should be getting about 1.4 across that one way, the laser diode way. And I do. Let's go ahead and zoom that out. And across the other way, I should be getting that Schottky diode voltage drop. Sure do. Okay, awesome. So we've got a way to read the voltage here, and I'm going to throw this meter in amps, reading the current, and place this in series with the laser diode and the output of the laser driver. Alright, we should be ready for the most part, so let's go ahead and put in power and signal modulation. That's on. Now, because the thermoelectric cooler is not running, nor are some of the heaters, yes, heaters on the inside of the laser head. Those aren't running either. We might get some output, we might not, but it won't be very efficient or very stable for long, but that's okay. Yeah, let's bring this up. Nothing, good. Let's turn up the current. See what we got. Alright, let's bring that up to like 8.5-ish. Actually, you know what? That looks pretty good, and we do in fact have some output. So at least the optical alignment should be pretty good. First part done. Alright, now that I have the constant current driver connected and ready to go, the next thing is to hook up a TEC driver. And here's one of the boards that I designed. This does heating or cooling, but not both. No H-bridge, and it has the current adjustment and the temperature adjustment for 2 TECs. So, let's go ahead, and the first thing I'm going to do is find the 2 wires that go to the thermistor that sits on top of the OPS chip, which will be 10K. So with the meter, let's go ahead and find what those wires are. And I spoke a little bit on how to use this driver board in the video where I converted a 473 nanometer laser into a 593. Alright, let's see what our magic wires are. That's one of the PTCs. So let's see what this wire is. Alright, that's my thermistor pair. So I'm going to go ahead and connect this up to the ground, which is here, and then my thermistor sensor input wire here. And it doesn't really matter which side you connect to which. Okay, I lied. It does matter if they have a common ground and you have more than one thermistor, but it doesn't matter in this case. Alright, the next step is to connect this to 5 volts. So let's go ahead and do that. For the time being, I am not going to connect the TEC because the next step is to find ambient temperature. Alright, that should be good to go. Let's go ahead and turn on the power supply. And then on here, I just want to set the temperature set point so that this light is on, but just barely. Alright, turn off the power, connect the thermoelectric cooler, ooh, that wire conducts more than electricity. Alright, now I'm going to turn on the power supply, and if the TEC polarity is correct, that light should come on and then start to go dim and off. Or it just starts off, that's cool too. Alright, that's configured correctly. Now, the OPS chip does need to be at a certain temperature to generate the right wavelength, which I believe is 1123 nanometers, in order to do the frequency doubling and get that 561 nanometers. Now, there is a little bit of a caveat. While you do need the correct temperature for that specific wavelength, there is a little bit of play in all the temperatures. So for example, if the OPS chip is a little warmer, that frequency is going to drift towards the 1150 range, and then if it's cooler, it's going to drift towards the 1110 range. So that plays a role in what wavelength you're going to get out of here. Once again, there's a little variance, but I'm not going to really pay attention to that temperature for the time being. Let's go ahead and connect the other thing, which is the PTC heater driver. Now, a PTC heater is one of these little things right here. And there are a couple of optics that require them to be a little warmer and held at a specific temperature. And those optics are the birefringent filter and then the second harmonic generation frequency doubling crystal. And the reason why they need to be kept at a specific temperature is that the birefringent filter works on refraction, and refraction changes ever so slightly with temperature. So basically the birefringent filter is just a narrow band filter which cleans up the light coming from the OPS chip and makes sure that it's very narrow band. So that's one thing. And then the second harmonic generation crystal needs to be held at a specific temperature so that it can do the phase matching correctly in the crystal. That's non-critical phase matching. You can go ahead and look it up. I talked a little bit about that in the last video as well. And these two wires should be the two PTC heaters. Let's go ahead and check. They should be about 100 ohms a piece, just like the PTC heater that I just showed you. So let's go ahead and show you on here. And this PTC heater is pulled from a Coherent Sapphire. I did a video on how to wire up one of those. So you can see about 100 ohms. And that's what we should see on each one of these pairs of wires. So that's one for the birefringent filter and the other for the second harmonic generation crystal. Now I have made a board to drive PTC heaters. It is a constant resistant driver and can run 4 of those PTC heaters. I'm just going to use 2 outputs, which is green and purple. You can connect these in whichever way you want. There's a couple of selectable outputs and selectable inputs for power rail and stuff like that. I'll talk a little bit more about that and how this came to be later on in the video. But for now, let's just go ahead and connect those heaters. Alright, and now I'm going to connect this up to the 12 volt output of the power supply. And that should be that. Everything should be all properly connected. The TEC, the driver for keeping that stable, and the 2 constant resistant drivers for those PTC heaters. So let's go ahead and see what kind of gains we get now that we have some control over the temperature of those elements inside of the laser. Alright. A laser driver is plugged in. Pump diode is turned up. Power supply is turned on. So let's go ahead and adjust these and see if we get better output than that. Can't read this in the dark. Alright, that one is definitely for the second harmonic generation. We're definitely getting a lot more output. Now when tuning a laser head that's DPSS or OPSL, there are going to be several different points when tuning the second harmonic generation optics. You'll get a bright peak and it'll go back down, and another bright peak and it'll go back down, and so on and so forth. There's usually about 4 different peaks, and the hottest peak is going to be in the middle area. So if you're tuning the temperature, keep that in mind. Don't just set it to the first brightest spot that you find. Alright, well, I need to find a fan, because I've reached the point of where the heatsink can do anything about the heat. After taking some time to adjust the temperature settings of the external TEC and the two internal PTC heaters, I'm happy to inform you that even though the original internal TEC for the OPS chip is non-functional, if you know how to run closed loop feedback to an external TEC, you can actually get these little laser heads to run with decently stable output. Now, another interesting fact is the color that you see on camera, which appears green, is not necessarily the color that you would see in real life. And this has to do with how the camera sensor picks up the frequency of 561 nanometers. And if you think that piece of information was interesting, you're going to like what's coming up next.
Let's dive into the core of the Obis Core LS. There's quite a lot of things happening inside of this compact laser head. To help you understand the pinout, I'll go over all the important parts that you need to know. The lasing process starts with 808 nanometer laser light created by an electrically pumped laser diode. Like with most laser diodes, the slow and fast axes diverge at different angles. To correct for this, a fast axis correction lens is mounted to the front of the pump laser diode's emitter. The laser light is then focused onto a point using a grid lens. Grid lenses don't work on physical geometry, but instead use a density gradient. The material in the center of the cylinder is denser than that of the material around the outer sidewall, which is metal plated. The term grid is short for gradient index, and it's a clever way to make small optics. The focused 808 nanometer laser light then hits the surface of the optically pumped semiconductor. These are specially tuned semiconductor lasers, but instead of being electrically excited, light is used for pumping the semiconductor gain material. For 561 nanometer production, the OPS converts 808 nanometers into 1122 nanometer laser light. 1122 nanometer laser light then travels through the birefringent filter, which narrows down the bandwidth, ensuring only 1122 nanometer photons reach the second harmonic generation crystal. Both the birefringent filter and second harmonic generation crystal are on small positive temperature coefficient heaters. This is because both of these optics rely on the rate of refraction in the material, which is partially dependent on temperature. Second harmonic generation is typically done in an anisotropic crystal, such as potassium titanophosphate or lithium triborate. In this laser, temperature is key to controlling this process, which means non-critical phase matching is used. 561 nanometer laser light, produced by the nonlinear optical process of second harmonic generation, then travels through the output coupler, where it is then reflected, collimated by a lens, passed over the optical pickoff sensor, and corrected on the horizontal axes by two prisms arranged in what's called an anamorphic prism pair. Finally, there's the optical pickoff sensor, which I am not using in this video, and since my TEC was open, I was unable to find the exact pins, but the traces seem to lead around to this side of the connector.
In some of the previous videos where I discussed the inner workings of laboratory lasers, I've gotten into detail about how to make your own constant resistance driver for the diodes and various ways of making your own closed-loop TEC controllers. But what I haven't discussed in detail are these positive temperature coefficient heaters. And the one video that I did is the Coherent Sapphire video. Now, in that video, I discussed this board that I came up with, which is a cycle-by-cycle constant resistance driver. And in a nutshell, how this board works is it would detect the resistance of the PTC heater, and if that resistance was too low, it would send out a burst of power. But it did these two functions separately, which led to a drawback. Now, of course, when it was doing the sense function, no power was going out to the heater, so the temperature would drop. And this board worked well at higher powers. However, at lower optical powers, it would generate a bit of a flickering as it went between those two functions. So I said to myself, there's got to be a better way of doing things. which led me to design this circuit. Now this is a very simple circuit, and I'm sure you'll understand how this works pretty quickly. So let's go over what components we have. It's an operational amplifier, a potentiometer, a semiconductor such as a MOSFET or an NPN transistor up here, a low value resistor, and the PTC heater right here. And essentially the circuit is just two voltage dividers. Let's go over what those two are. Over here on the negative, we have one voltage divider that comes up this way, goes through this potentiometer, and then from the other side we can follow it straight down and see that it's on the positive. So our sweeper here can be set by the potentiometer anywhere from 0 volts all the way to our input voltage, which is one voltage divider. The output of that potentiometer goes to the inverting input of your operational amplifier. Now I recommend that you use a potentiometer that is 10K or higher, simply because if it's too low, this could get warm in of itself due to the power going through it, and that might change your temperature calibration if that warms up. Our other voltage divider is through this section right here. So that starts over on the negative side, comes up this way, and then goes through this semiconductor right here. As I said, you can use an N-channel MOSFET or you can use an NPN transistor, and it's labeled as such. Your input being either the source or the emitter, your output being the drain or collector, and then your signal input from the positive output of the operational amplifier going into your gate or your base. From there, that power goes through this resistor, which forms the half of the voltage divider coming from the negative side, and then through this way down through the PTC heater, which acts as your resistor on the positive side. Now how this circuit works is, if the resistance down here is too low, it will continue to send power through this whole loop, and the resistance that is from positive to this point right here is monitored by this wire. So as you can see, it's between the resistor up here on the top and then the resistor down here on the bottom. So as this warms up, the resistance raises and the voltage at this point changes. That change in voltage is detected by the operational amplifier on the non-inverting input. So it's a very simple circuit to use. And this is what the circuit looks like when it's on a breadboard. Now you notice that I have some extra parts here, and that's pretty simple to understand as well. You have a smoothing capacitor, a voltage regulator, and then the output of the voltage regulator, once again smoothed by another capacitor on the output. And the reason why I have a voltage regulator is for two reasons. When you're dealing with any sort of comparator or operational amplifier, it is good to have a voltage reference. So that way the voltage on this voltage divider here and the voltage on this voltage divider here doesn't change. Of course, you want this to remain stable, so that way your temperature set point also remains stable. And for that, I'm just using a 9-volt regulator, the LM7809. Over here is my operational amplifier, my potentiometer, the switching transistor, and the resistor. So pretty simple circuit. Very simple board to make. Now this resistor here, that resistor is actually between the positive and the input of this potentiometer. You don't need that resistor, so that's why I haven't drawn it in, and I didn't even put it on the new boards. Very, very, very handy. So if you need to drive PTC heaters and you need to do it in a very stable way, such as for laser applications, this is a good and simple circuit to use. So Obis Core LS brings together two of my favorite things, lasers and miniaturized technologies, and I've wanted one for as long as I've known about them. However, they come with the same drawback as most laboratory used lasers, and that is they are prohibitively expensive. So why would someone spend 4 figures on a laser that doesn't even burn? Well, in this case, it's not just about the wavelength, but also spectral purity, low bandwidth, and long coherence length. To help you understand what those terms mean, Let's start with something that doesn't have any of those things. A flashlight. Time to show you a simple test that you can do to determine some of the properties of your laser. And all you need for this is a relatively clean microscope slide. Now I'm going to start off showing you how to perform this test with a flashlight. And to do this test, all you need to do is shoot your source of light towards the microscope slide like that. And it's actually going to be the reflection off the microscope slide that we're going to be taking a look at. Now, of course, with this, if you take a look at the reflection, it's pretty much what you'd expect. Nothing weird going on yet. But things are going to get really interesting the lower we go in bandwidth. With that said, let's take a look at three lasers. The first laser we're going to take a look at is this 500 milliwatt, 650 nanometer multi-mode diode laser. We can see our output here on the wall. Now, in order to do this test, the output of the laser needs to be expanded. And to do that, I'm simply going to tape on this little positive meniscus lens on the output aperture of the laser. And here's our expanded output. I am going to change the camera settings and turn off the light, and we can see what that laser output looks like in more detail. And that's what the output looks like coming right off the module and then through that expanding lens. So now I'm going to flip the laser towards me. We're going to take a look at the reflection that comes off the microscope slide. And there it is. So of course it's dimmer, but besides that, there's not much really going on. Let's check out our next laser. The second laser we'll be taking a look at is this 50 milliwatt, 520 nanometer single transverse mode laser diode, which has a much more narrow bandwidth than a multi-mode laser diode would have. So same thing for this, we have to expand the output, which I'll simply do by adjusting the focus of the front collimating lens. And there's the expanded output. So I'm going to turn off the light and we can take a look at what that beam looks like in a little bit more detail. That's pretty nice. Pretty even. So same thing as before. I'm going to turn the laser now towards me. And let's take a look at the reflection off the microscope slide. And there it is. Now you'll notice that there are now light and dark bands that are present in the reflection. And that has to do with the interference of the two reflections coming off the microscope slide. The first reflection is of course off the front surface, and the second reflection is coming off the surface that's actually in the glass. So that's what pretty low bandwidth looks like. But what about if we go even further? Finally, let's talk about the last laser, which is of course the Coherent Obis Core LS. Now the previous laser that we just took a look at was a single transverse mode direct diode laser. And what that means is that there was only one mode of oscillation that was perpendicular to the output of the laser beam. However, there's also another mode of oscillation, and that is along the same axis as the output of the laser, and that's your longitudinal mode. Now we saw the improvement in spectral purity when we had a single transverse mode, but if we also have a single longitudinal mode, the bandwidth also is lowered even more significantly. And this laser is either single longitudinal mode, what they call SLM, or really close to it. So once again, I'll put a lens on the front of the laser so we can see the expanded beam. And we get a very nice, round, perfect Gaussian output. Very speckly as well. So you can already see that there's some improvement. So same thing, I'm going to turn the laser around towards me, and we're going to reflect the laser back off the microscope slide. There it is, the wonderful interference patterns off the microscope slide. Once again, this is because there are two reflections, the first reflection coming off the front surface of the microscope slide, and the second reflection coming from the other side. And you'll notice just how much of a difference there is between the dark and bright bands. So if you see this from the reflection of your laser off a microscope slide, congratulations, you have a pretty low bandwidth laser and probably a very long coherence length. But yeah, a multi-mode diode laser won't do this. It's simply not good enough, and few lasers are.
Here's a simple diagram showing how different longitudinal modes are generated in a resonator and why coherence length can be lost in such a short distance. And I've also made this diagram to help you understand how the microscope slide generates interference patterns. However, in reality, reflection angle and the thickness variations in the glass also play a role. Now, while burning lasers are really cool, I hope you better understand the other qualities in a laser beam. A 500 milliwatt multi-mode laser diode pointed at my wall makes my shop look like this. However, a 50 milliwatt single longitudinal mode optically pumped semiconductor laser does this instead, which demonstrates the spectral purity used in many scientific applications. Holography is another industry that requires narrow bandwidth lasers, and one was used in the production of this hologram, of which I bought from SmirHolo several years ago. The Coherent Obis Core LS. It's a small laser with a large range of applications, a source of highly specialized photons specifically for exploring the intricacies of the world around us. The kind of photonics technology rarely seen in operation and yet continues to play crucial roles behind the sciences we rely on every day. I hope that you've enjoyed learning about this miniaturized marvel of technology, and those of you who may be lucky enough to have acquired one of these for yourself, may this video have been a suitable guide to helping you get yours running with the same success. Getting lasers like these operating has been a passion of mine for years. As I have grown in knowledge, I have been doing what I can to make information available, and I have also been developing laser driving hardware that one day I hope will help others do the same. If you want to help myself and the laser community grow, do consider donating to the cause. And as always, stay tuned for more.
Huh, well, what do you know? It is capable of, in quotation marks, burning things. That's okay by me.